Welcome! For today's lesson, we are going to be discussing subgroups. As a reminder, by a group, we mean a pair G, circle, such that G is a set together with a binary operation circle on G. And we have that the following four axioms are satisfied. We have closure, that if we take any two elements A and B in G, whenever we take A circle B, we're back in G. And so A circle B is in G for each A, B, and G. We have associativity. The order of the parentheses do not matter. If we have A, B, C, and G, we will always have that if we take A circle B, then C, that is the same as doing A first and then parentheses B circle C. We have identity. There exists at least one element E in G that satisfies A circle E equals E circle A equals A for every single element A in G. And we call E the identity of the group. And finally, we have inverses. That for every single element A in G, there is at least one B in G such that A circle B equals B circle A is equal to the identity. As part of the first homework assignment, we now know that from the axioms we can prove that this at least one element E in G is in fact exactly 1, and so the identity is unique. Similarly, the additive inverse of an element A is unique, and so this warrants the notation whenever we're talking about the inverse of an element. We usually write A to the -1 or say it A inverse. And finally, we say that a group is an abelian group if we have commutativity. That if we were to take A circle B, that is the same as doing B circle A for every single A, B, and G. And now we are ready to define the notion of a subgroup. So let us suppose we have a group G, and whenever I say a group G from now on, it's implicitly understood that I really do mean a pair G, circle, where circle is the binary operation on G. So let us take a non-empty subset H of G, and we say that H is a subgroup of G if H is closed under products and inverses. If this is the case, we write H is less than or equal to G, which we now read as H is a subgroup of G. Now, this portion over here, that it is closed under products and inverses. What this means is that for every single x and y in H, we have that x circle y is back in H, and for every x in H, we have that x inverse is in H. And this brings us to the subgroup criterion, which allows us to determine whether a given non-empty subset H of G is a subgroup. And so the subgroup criterion tells us is that if we have a group G with identity E, and H is a non-empty subset of G, then the following are equivalent. H is closed under products and inverses, is equivalent to x circle y inverse is in H for every x, y in H, which is equivalent to H being a group. The takeaway here is we can verify that a non-empty subset H is a group by checking that it is closed under products and inverses, or x circle y inverse is in H for each x, y, and H. Let us see this in action. So let us take f to be the rational numbers, the real numbers, or the complex numbers. And by GON of f, we will denote the general linear group of degree n. That is, those matrices, those n by n matrices with entries in f such that the matrices are invertible. And that's going to be a group under multiplication. And we're going to define the special linear group of degree n, which we denote by SLN of f, to be those n by n matrices in GON of f. So in other words, A is invertible by being in GON, and its determinant must be 1. And so that's the condition to be in SLN of f. And we want to prove that the special linear group of degree n is a subgroup of the general linear group. Well, we know from the subgroup criterion that if we prove that the special linear group is closed under products and inverses, then we are done. It's a subgroup. And that's exactly what we do. But first we need to verify that the special linear group is non-empty. But that's easy. Because if we take the n by n identity matrix of GON, that has determinant 1. So it's in the special linear group. And so we know that it is non-empty. Now let us take two matrices in SON of F. And so since they are in SON of F, their determinants must be 1. And if we take the product of A and B, then the product of the determinant of the product is going to be equal to determinant of A times determinant of B, which is now 1 times 1, and so we get back 1. So in other words, A times B is in fact in the special linear group of degree n. And so now we have shown that it is closed under multiplication. Let us check now that it is closed under inverses. So we take our matrix A in the special linear group, and we take the determinant of A inverse. But the determinant of A inverse is the same as determinant of A, and then to the negative 1, so the reciprocal of the determinant of A, but that's 1 to the negative 1, which is just 1. So that tells us that that A inverse is in the special linear group of degree n. And so we have shown that it is closed under inverses. And consequently, by the subgroup criterion, SON of F is in fact a subgroup of GON of F. So we have proven that SON is always a subgroup of GON. But how do we go about finding other subgroups of GON? There are others. For example, we have the classical groups of GON, which you may encounter in the future if you have not done so already. We have the orthogonal group, the unitary group, and the symplectic group. But a good strategy for finding other subgroups is through the method of conjugation. And so here is the proposition. So let us take a group G with identity E, and let's say that we have a subgroup H. So in the example we just did, we now have G is GON, H is SON. And what this proposition tells us is that for every element G in the group G, we can define the conjugate of H to be G circle H circle G inverse. And now keep in mind G is an element, G inverse is an element of capital G, and H is the set. And the way that we interpret this notation is that we are acting on every element of H via this process of taking G on the outside and then G inverse on the right. And so this is the set of all elements of the form G circle H circle G inverse such that H is an H. And what the proposition tells us is that G circle H circle G inverse is also a subgroup. And so now we have a method for constructing new subgroups of a given group G, so long as we know that we have a subgroup H to begin with. So why does this hold? Well, the subgroup criterion is the key. We want to show that it is closed under products and inverses. So we have H as non-empty by assumption, since it is a subgroup. So let us choose some X and H. Then what we have is that if we take G circle X circle G inverse, this is in the conjugate of H. And so we also have that G circle H circle G inverse is non-empty. Now let us take some arbitrary elements X and Y and H. We know that since H is a group, X circle Y is an H. And now what we are going to do is take their conjugates and take the products of them. So we take G circle X circle G inverse, circle, and then G circle Y circle G inverse. But G inverse is the inverse of G. And we have associativity since we have that all of these operations are happening inside of G, the group G. And so moving things around for the parentheses via associativity, we have G circle G inverse, that's the identity. And so now we have G circle X circle Y circle G inverse, but that is by definition inside of the conjugate of H. And so we have shown that it is closed under products. So next we're going to show that the conjugate of H is closed under inverses. So to that end, we know that our X is in H, so X inverse is in H, since H is a group. And we're going to take G circle X circle G inverse to the -1. But this is going to be G circle X inverse circle G inverse, and that is the inverse, and by definition, it is going to be inside the conjugate of H. So in other words, we have demonstrated that the conjugate of H is closed under products and inverses, and therefore it is a subgroup of G. And that gives us now a recipe for finding new subgroups. So how do we go about constructing more subgroups of a given group G? Well, this brings us to the notion of centralizers and normalizers. So we have our group G, and we are going to consider the power set of G, that is the set of all subsets of G. And so let's take a subset A of G, and we define the centralizer of A in G to be the following set, which we denote by C sub G of A. And it consists of all those lowercase g's in the set G, such that G circle A is equal to A circle G for every single element A in the subset A. Now, observe that we have G circle A equals A circle G, and this is reminiscent of commutativity. And so another way of phrasing this is that the centralizer is the set of all elements in G which commute pointwise with elements in A. Another way of viewing this that goes back to what we just discussed in terms of conjugates of H is that if we look at this equation here and then take circle G inverse on the right on both sides, then we get G circle A circle G inverse, and then G circle G inverse is going to give the identity, so we get back A on the right. And so we got this equation right here. And so we can phrase the centralizer of A in G to just be the set of all elements that satisfy this equation for every single A in A. Another statement that we have in terms of subsets of A is the normalizer of a set A. And the normalizer of A in G is denoted by n sub G of A. And it consists of all those elements G and G, such that G circle A is equal to A circle G. And so now, if we take G inverse on both sides of this equation, we have G circle A circle G inverse equals A. And so that's another way of viewing the normalizer. And so this is the set of all elements in G which commute with A as a set. And that's the key distinction. Over here we have the lowercase a, here we have the capital A. And so what this is saying, if we think about it in the following way, that G circle A circle G inverse is equal to A, that is going to tell us that for all A in A, we have that G circle A circle G inverse is back in A. And so that will give us back an element in A. And so that's the key difference between normalizer and centralizer. The centralizer will force us to be exactly equal to the A that we have here, whereas the normalizer is a weaker statement in that it just needs us to be in the set A upon taking this product. And the following proposition tells us that both the centralizer and normalizer of a set A are subgroups of G. And we have the following subgroup containment. The centralizer of A is a subgroup of the normalizer of A, which is a subgroup of G. And the centralizer of A is a subgroup of the normalizer of A. We see that in this notion that I just mentioned in terms of the normalizer being a weaker condition, whereas here we require this to be exactly the same A. So to start off, let us do two quick examples of normalizers and centralizers. So we have two non-empty subsets of G always. We have the set containing E and we have G itself. If we take H to be the set containing E, then we have that the centralizer and normalizer will just be G. Because if we come back to both definitions, in the case of the centralizer, we have G circle E is equal to E circle G. That's always going to hold true for the identity, since in this case, we have that the capital A is our set containing E. And so we will get back every element in G back. And similarly for the normalizer. And so here we do have this property here. Now, if we take H to be the whole group G, then the normalizer of G will be equal to G, because G is closed under circle. So come back down over here. We're looking at the normalizer of G in G, and this is the set of all elements in G, such that G circle G, and if we view it this way, so G circle G inverse lands us back in G. And so since everything is closed under products, we have that the normalizer of G will be G itself. Now the same is not true of the centralizer. If we take the centralizer of G, it is not necessarily going to be equal to G, because now we will need that G circle any other element A in G is equal to A circle G for all the elements in G. And so in other words, we're looking at all the elements in G that commute with elements in G. And there is a notion of this known as the center. And so the centralizer of G and G is called the center of the group. And it's the set of all G's in G such that G circle X is equal to X circle G for every single X in G. Something to observe is that the center of G is exactly equal to the G when the group is abelian. That is, we have that the commutative property holds. Because if the centralizer of G is equal to G, then we are saying that we have all the elements in G commute with all the other elements X's in G. And so as a proposition, we get the center of G is a abelian subgroup of G. Before getting to the next example, let us come back to the conjugate of H. So I'm going to introduce some notation. So I'm going to use G dot H to denote the conjugate of H. And so this will just be shorthand for G circle H, circle G inverse. And now what we are going to do is consider the symmetric group on three letters, which was introduced in the last lesson. It is generated by the elements R and S, where R is a 3-cycle 1, 2, 3, and S is the 2-cycle 2, 3. Let us consider the set A to be the set generated by R. And so this is the set consisting of R, R squared, and then we get to R cubed, which is 1. And this set is just the elements 1, then the 3-cycle 1, 2, 3, and the cycle 1, 3, 2. But we are also going to consider the set B to be the set generated by S. And so in this case, we have S is equal to the cycle 2, 3. But if we do S squared, we get back the identity permutation. And so B is just the set consisting of 1 and 2, 3. So both A and B are subgroups. And what we are going to do is use the notion of the conjugates of A and B in action. So we're going to do G dot A for a given G. And so in the first example we are going to consider, we're going to take G to be R. And so here we have R circle R circle R inverse. And so if we do this, we're going to get back the element 1, 2, 3. And if we do 2, 3, then R, and then S inverse, this is going to give us back 1, 3, 2. And I encourage you to pause the video and do this calculation using permutations as we discussed in our last lesson to verify that this here is in fact 1, 2, 3, and this here is in fact 1, 3, 2. So what we get from both of these calculations is that since 1, 2, 3, 1, 2, 3, 1, 2, 3 inverse, since this gives us back 1, 2, 3, we have that 1, 2, 3 dot A is going to be exactly A. And similarly, by taking S dot A, we're going to get back A since it left 1, 2, 3. It sent it to 1, 3, 2, which is in A. Now, it still leaves the question of what's going on with 1, but with 1, we put it in here. This is just going to be 2, 3, 2, 3 inverse, and so that gives us back 1. And so we do in fact get back that the conjugate of A via 1, 2, 3, and 2, 3 is back to A. Now let us consider B. With B, it's a bit different, because if we take R, so now we're taking R, and here's S, and here's our inverse. In this case, we're going to get back 1, 3. But 1, 3 is not in this set. And so in other words, 1, 2, 3 dot B is not equal to B. It is in fact going to be equal to 1, comma, the cycle 1, 3. And now we have a new subgroup of the symmetric group on 3 letters. However, had we done S dot B, then we will have S, circle S, S inverse here. When we do this, we're just going to get back 2, 3. So we will get that 2, 3 dot B is in fact equal to B. So now let us consider the normalizers and centralizers of A and B respectively. So by definition, the centralizer of A is those elements in G such that G circle A is equal to A circle G for every A in A. In our work up here, we already showed that if we took S, then R, then S inverse, that is 1, 3, 2, which is not 1, 2, 3. Therefore, S is not in the centralizer, but it is in the normalizer of A. Because for the normalizer, we just have to be back in the set A, and we have that 1, 3, 2 is in A. And so S is in the normalizer, but not in the centralizer of A. Continuing, we did not do R squared, which is going to be 1, 3, 2. But if we took 1, 3, 2 and applied it to 1, 2, 3 and 1, 3, 2, we will get back the same element. And so the centralizer of A is just the group generated by R. So in other words, we get back A. Whereas with the normalizer, we are going to get back the symmetric group on 3 letters. Now, if we look at our set B, which is just the group generated by S, and so the element's just 1 and the 2 cycle 2, 3, in both situations, we're going to get back that the centralizer and normalizer is B itself. Now, keep in mind that when we did our work just now, we saw that we took 1, 2, 3 dot B, then this did not land us back in B. And so we know that 1, 2, 3 cannot be in the centralizer nor normalizer. But S is in here and here. Now, S3 is a non-commutative group. And so its center in this case is not going to be the whole group, because if it were, it will have to be abelian. And a computation shows that the center of the symmetric group on 3 elements is in fact just the trivial permutation, the group generated by the trivial permutation, so in other words, the trivial subgroup. Similarly, if we take the centralizer of A and the centralizer of B, they are going to be disjoint except for the trivial permutation. So their only intersection is just 1. And we see that from the work we have just done. The centralizer is B, the centralizer of A is A, and in both of those cases, if we take A intersect B, we just get back 1. So let us transition towards cyclic groups. The group generated by R has only 3 elements. 1, the trivial permutation, then we have R, and then we have R squared, which is 1, 3, 2. We are going to go ahead and extend this notion further, and so we're going to say that a group G is cyclic if it can be generated by just 1 element. So in other words, there exists some x in G such that for every element G in the group, we have that G is equal to x to the a for some integer a. And in this case, we say that x is a generator for G and simply write G as bracket x. As an example, let us take n to be greater than or equal to 3, a positive integer, and let us consider the regular n-gon, which we define in terms of its vertices to be cosine 2 pi k over n and sine of 2 pi k over n as k ranges through the integers. Since this is an n-gon, this is just going to have n vertices, p1, p2, all the way through pn. Then we have the linear transformation R, where now we view R as a linear transformation from the plane to the plane. And so R can be given the following matrix representation. So we have cosine 2 pi n, negative sine 2 pi n, sine 2 pi n, cosine 2 pi n. This matrix, if we take it to the nth power, it's going to just be exactly the identity matrix. And so we come back to in other words, we take pk, we send it to pk plus n, we get back pk. And so here we have the group G, where G is generated by R, and we have the elements of the group are just 1, R, R squared, all the way to R to the n minus 1, because once we get to R to the n, we cycle back around to the identity until we get back 1. Now, the generator of a group it's not necessarily unique, because we took R, but we could have also taken R inverse. And that's also true in the previous slide. We took R here, but had we taken R to be 132, we would have had that 132 would have still generated the group A. So let us generalize. So let's start off with a group G, and let A be any subset of G, including the empty set. And we're going to let calligraphy A be a family of subgroups. And so this calligraphy A is defined as the set consisting of subgroups H and G, such that H contains A as a subset. And we're going to define the subgroup of G generated by A, which is we're going to denote over here by bracket A, to be the intersection of all the H's in calligraphy A in the family of sets. And so we're just taking those intersections. And so that's going to be a subgroup. And moreover, if we have some list of subsets A1, A2 through AK, then we can define the subgroup of G generated by each of these A1s, A2s through AKs, possibly a denumerable list, to be the subgroup of G generated by now taking the union of each of these. And so the key thing in this notation is that now we have our subsets, A1, A2 through AK. We take the union. And so now this here is going to give us a new subset of G. And now to find the subgroup of G generated by A, namely this, we come back over here and we take the intersection of all those subgroups that contain A. And so the proposition is that if we have that G is a group and calligraphy A is any non-empty collection of subgroups of G, then if we take K to be the intersection of H, where H is in the family of subgroups, then K is also a subgroup of G. The next statement is if we have that G is a subgroup and A is a subset of G, then the following sets are all equal to each other. If we take the subgroup of A, the subgroup generated by A, which is, as we just defined, the intersection of the subgroups containing A, then that is going to be equal to the following, which we denote by A bar. And so this is going to be A1 to the epsilon 1, circle A2 to the epsilon 2, and then we just go through, continue to take products with each of the elements over here, where now each of the A sub k's are in A, and the epsilon k's are either plus or minus 1. And similarly, A underscore here, this one, is going to be A1 to the alpha 1, product with A2, alpha 2 circle, and we just continue, AN, alpha N. And now, as before, the AKs are in A, but now AK does not equal AK plus 1, and the alpha Ks are all integers. And so you'll have opportunity to tinker around with this proposition as part of the homework. But what does this notation mean? So if we look at A bar, this is consisting of all the elements in A, and then we're taking the products of all of them with themselves, also including their inverses. So we have A1 to the 1, and we can just have A2 to the 1. And so now we have the product of all the elements that are in the set A. Similarly, we could have A1 to the negative 1, and then take A2 to the 1, AK to the 1, and then AN to the 1. And so we're just looking at all the possible combinations. So we're putting in all the elements in A, and then adding in all the elements that would require it to make it a group. In other words, we're forcing it to be closed under multiplication and inverses. And that is better seen with this notation here. Because now what this is telling us is that we can take alpha k to be an integer. So we can take alpha 2, alpha k, alpha n, each of these to be 0. And then we just have a1 to the 1 is in there. But we also have a1 squared, a1 cubed. We also have a1 to the negative 1, a1 to the negative 2. And so that will also be in here. And then we can alternate and then make this a 0, make this a 1, keep the rest as zeros. And we would have that now a2 and everything generated by a2 is in there. And so this now is the explicit way of visualizing what this subgroup generated by A actually is and how it looks like. So now let's look at a definition. So we have G as a group. We have A as a subset of G. So we have just seen that these three sets are equal. Well, we haven't proven it, but this proposition tells us that they're all equal. We call this the smallest subgroup containing A. And the elements of the form A equals A1 alpha 1, A2 alpha 2, and then circle all the way to AN alpha n, where now the AKs are in A, alpha Ks are in the integers. These are what we call words. And the identity element is called the empty word, and it corresponds to the case where each of the alpha j's is equal to 0. So now let us do a few examples based on the terminology we just discussed. If we have that A is the empty set, then the smallest subgroup containing the empty set is just the trivial subgroup, the group generated by the identity. Now, if A is equal to the set containing X, where X is just some element in the group G, then the group generated by A will just be the group generated by X. And so the cyclic group generated by X. And so here we'll have x1, x squared, x cubed, x to the fourth. We'll also have x to the negative 1, and consequently we'll have x to the negative 1. They are going to be in here, and so when we take the product of the two, we get back the identity. And so the identity is in here. And more generally, if we have that A consists of this finite list of elements of G, x1, x2 through xn, then F sub n, which we denote to be the group generated by x1, x2 through xn, we call this the free group of rank n. In the case of the dihedral group, which we have as the group generated by R and S, where R to the n is equal to S squared, which is equal to 1, and we also have the second relation, SRS is equal to R inverse. This is the group generated by the set A, which is equal to this just consisting of R and S. And in the general setting of the symmetric group, it is always going to be generated by the 2 cycle 1, 2, and then the n cycle 1, 2, all the way to n. So here are some more examples. Let us take G to be a finite group and A to be the set containing A1, A2 through AN, and these are all elements in G. If G is abelian, then the group generated by A, which is A1, A2 through AN, its order is going to be at most the product of the orders of A1, A2 through AN. And so here we're using a certain property of finite groups, that if it's finite, if we take some element A1, then we do A1, then A1 squared, A1 cubed, A1 to the fourth, there will be some integer k such that A1 to the k is the identity. And so each of these will be some positive integer, and we're taking the product of them. And that gives us a bound on how large the group generated by these elements A1 through AN is. But it is crucial that we use the fact that G is abelian, because with Sn, the symmetric group on n letters, this is not the case. So to illustrate this, let us consider the symmetric group on n letters. Its order is n factorial, but we know that it's generated by the 2 cycle, which is just 1, 2, 1, 2, but that's just order 2, because if we take 1, 2 squared, that's going to give us back the identity permutation. So this has order 2, but then the n cycle will have order n, and so the product will just be 2 times n, and the group has order n factorial. And so this statement only holds when the group is abelian. Let us return to the special linear group, but now with entries in the real numbers. And let us consider the set A to be the set consisting of the matrices R and S, where R and S are as defined here. So one can verify that if we take R to the 6th, that's the identity matrix, S to the 4th is the identity matrix. So that tells us that the order of R is 6. The order of S is 4. However, if we take the matrix T to be x cubed times R, then we get that T to the n has infinite order, because we're going to have 1 and 0, 1 for all the n's in the integers. And so this does not have a finite order, so now the group generated by A would be an infinite group. And in fact, the group generated by A is the special linear group with integer entries. Thank you for watching.